Did you go on to the stream last night? To the streaming platform? You know how to do it? The link is on the syllabus. Any luck? You know how to do it? We got some. Thank you. Is it working? Can you see an image of the screen reasonably well? All right. Thank you. Say again.
You were
Weird. I guess we'll have to work. It's weird. It's a different problem every day. How's it look now? Oh, all right. We got to move on, I guess. Thank you. Any luck? Why is it? It's just showing there's energy.
I don't even, I think it's just showing us like behind the like it's the truth.
Sorry, everyone. Okay, well, we'll press forward. Hey everyone, sorry for the delay. So I came across this image the other day and I was like, oh, this is a great example of like turbulent flows. So this is an aerial view of a freighter and a small boat next to it. And you know, you can see these little more technical difficulties. Sorry, Brian. Well, I apologize. Here we go. So you can see these little rivulets here along the sides here. And so, you know, in the really long boat, basically what's happening is the energy of the water that it's displacing is a massive amount of water, but that inertial energy essentially is being displaced along the whole axis of the boat. And you can see these little rivulets. And that's what happens along the back of, like, say, a tuna or a mackerel, you know, those finlets that we saw, the scutes, those help to displace that energy and allow it to move more quickly. And so the longer a boat you have, just like the longer a fish you have, the less energy it takes to move through the water. And you can see what happens with the little boat here. It just develops this massive, essentially the water goes around it and comes in around and it creates these like eddies behind it, like this, which pull the boat backwards. So anyway, length and a long torpedo-like shape make a difference both in you know, the technologies taken from fishes, I guess you could say. So today, I want to review the fish account paper, which is going to be due on October 13th. I want to finish up anatomy and physiology. Today will be the last day for that. And then we'll get into some different stuff, more evolution, conservation type themes, which I think you're waiting for. Yes, I will make it to the participation assignment today. A lot of you asked me, there was none for the last lecture because I didn't get to it. And then next week, we'll talk about fish evolution and ancestral fishes. We'll talk a little bit about how to do research for your paper, and also we'll have a guest speaker on shark conservation. So the paper, so try and do a good job on paper. It's worth about 15% of your grade, which is a big chunk. It's 10 points for the draft, which is due on the 13th. It's another 10 points for the peer review that you do of the draft that you received, because essentially we've got it set up in Canvas, so you'll submit your draft on the 13th, and then it'll get shot out to 2 of your peers. They'll peer review it and then send it back, and each of you will get 10 points for your contribution to that process. And then the final version is where the hotter points. So the draft can make a big deal. And we need to get it to you on time, or we need to get it to us so we can get it to you on time. So there are no late drafts going to be accepted. If you submit it late, you're not going to get credit for it, because it totally buggers us out in terms of getting, it's a lot to actually negotiate 135 different papers being sent to 2 people and then getting it back to the original author. So on time or not at all. And I think that all of you can handle that. The thing is, with writing, it's not a super complicated paper. It's just a species account, you know? So the thing is to like find 15-page papers or stuff in the peer-reviewed literature, sit down, cruise through the abstracts and the figures, dig into the text where you need to, enjoy yourself, exploring something about a fish that you're interested in, and then kick back and start taking some notes. And you know, as you read, taking notes is useful. When you go to set up the paper, an outline can be helpful. If you have a bunch of notes that you've taken, you might be able to construct an outline. And in the assignment, I help you do that. I'll talk it over with you in a few minutes here. But the key thing is not to get hung up by the writing. The key thing is just to start writing. You know what? When I write, I stole this idea, but what I do is I basically start out with "Dear Mom," because you know my mom loves me, and I could I can send Mom a really crummy draft, and she'll be like, "Oh, I still love you, son." And so so I know that sounds super crazy, but John McPhee, the great nonfiction writer John McPhee, who wrote a lot on California geology, animals of the former world, and conservation issues. Encounters the Arch Druid, someone you might want to check out. John McPhee, that's his mode too. So if it's good enough for John McPhee, it's good enough for me. And it's anything to get over the self-criticism. I feel like, like when you sit down to write, there's like this internal radio station in your head that stops playing music and it turns to radio KFKD. And radio KFKD just tells you what a terrible person you are and what a crummy writer you are. And you just have to blow past that and start writing. Dear Mom, if that's what it takes, start writing. Start writing, get the draft in. Doesn't matter if it sucks, as long as the draft is in, you're gonna get some, hopefully, professional criticism, and that'll help you improve it. So we've got like 3 steps along the way to help you get in a decent paper. Make sense?
Yeah.
Okay, cool. If you haven't already, you need to sign up for a species, which the link is here on the slideshow. You can get it. You can also get it off of Canvas. Seth talked about the drafts already. Continuous line numbers. So if you go to, this is like to bugger people up. I actually posted a video, which is on Canvas, which is John's hot tips for posting or for putting in line numbers and for using citations and a citation manager. And it's only a few minutes, and it'll help you organize your citations and your references and figure out how to do line numbers, okay? So basically it's, the instructions are right here. The reason for line numbers, and you want it to be continuous, is that your peer reviewers are gonna need to reference parts. They're gonna write a document in response to your paper, and they need to reference parts of it. If they have to say, oh, page 3 on the 3rd paragraph down, halfway in, it doesn't work very well. So use continuous line numbers so that we can reference it. Your paper should be single spaced, about 3 to 5 pages, not counting figures. We want it to be publication style, so include some nice figures, some maps, pictures of the fish, pictures of the habitat, the morphology of the fish, any kind of graphs or plots you want to include. Use at least 15 references. And in your citation style, you want to use the American Fisheries Society style format. And you can get a link for that on the assignment page in Canvas. There's a link for that format, and you can review it. Or you could go to John's Hot Tips and figure out how to use Zotero, which is a open source citation manager that I use for keeping track of all my thousands and thousands of references. I started it years ago because I thought, well, someday I'll leave the university and I want to take my papers with me. And here at the university, we've got like access to everything, right? So I kept everything and I stored it in Zotero. As it turns out, I guess I'm stuck at the university forever, so it's not such a big deal, but I still download things and I keep track of them so that I can do my own searches with papers that I know and I'm familiar with. If you want, you can also use EndNote, but I think EndNote is proprietary and basically, I don't like it very much. So I recommend using Zotero. It'll save you tons of time now and in the future. If you have questions about it, hit me up. Office hours, send me an email, whatever. I'm around. So the paper itself. This is what we want. First, species description and figures. So what does the species look like? What size is it? The key anatomical figures that distinguish it from other species, and what species might be confused with it and how you tell the difference, right? Are there any differences between the juveniles and the adults? What is the developmental stages that the species goes through? Include all of that. And you can use pictures that you find on the internet, and you just have to cite everything, because this is the great rule of academic plagiarism. You can't use stuff without citing it unless you're a prof and you're trying to put together a slideshow really quickly for a lecture, and then you just steal and pirate and you just hope that nobody calls you out on it, right? So like me, you'll see I don't bring my citations. But for publication or for citation in a class, you just have to do it. The geographic range of the species is going to be very critical. You can find maps of the species range, species distributions. Again, you just need to cite your source. Also, on a more granular scale, what types of ecosystems and habitats is it found? Is it abundant? Is it rare? You know, where is it abundant? Where is it rare? Why is it rare? The biology of the fish, reproduction, age, growth, food and feeding habits, and anything else that's interesting. And finally, conservation status. List and discuss the conservation status of the species. Is it stable, declining, extinct? You should be able to find a lot of information about some species, and some they're just data deficient. It'll be much more difficult to find out information. You can always switch if you need to switch. If another species is open, if you just can't get enough references, you might want to, make it easy on yourself. Also talk about fisheries. If there's a fisheries for the species, discuss that. If humans utilize it, discuss that. There's cultural importance, also hot topics. So if you think about it, there's a tons of stuff that you can include in this 3 to 5 page paper that can fill it up pretty quickly. It won't be enough room. The trick will really be to kind of condense it so that in clear, simple language. Clear, simple language. So one of the evils of the scientific literature is how people write. They use jargony words, a lot of $3 words with lots of syllables. And the reason they do it is because they want to sound smart. Because if you sound smart, well, good chance of getting published. And it's just all nonsense. We're trying to break through that wall of the ivory tower. I think culturally, it's a good moment. But don't do that. Clear, simple language is a beautiful thing. And it sounds much more impressive if you have an idea that you can explain clearly, as opposed to trying to put up a firewall around your niche, like all these old white guys did for so many years in academia. So there's published examples and student examples of this on Canvas. You should be able to see it in the module for this week and in the files. Check it out. Check out my hot tips. It'll save you time later. Any questions about the paper? Yes?
What format is it in? Like MLA or?
American Fisheries Society. You mean the citation format?
Yeah.
Yeah, American Fisheries Society. They have a series of journals and they have their own proprietary format. And so if you go onto Canvas and for the assignment, it'll show you a link to that style, or you can use Zotero and download the citation style. I show you how to do that and it'll format automatically for you.
Okay.
Yes.
Will there be like an example paper to see how like a paper like this would be written?
Yeah, I just said that in the assignment. Let's see, where did I say it? There, right there in front of me. Both published in Student Examples are right there in Canvas.
Yeah.
Yeah, I was spaced out too because I didn't know I had it in front of me either. So anyway, yeah, look those up. I'm not going to splash an example of it because I know you can do that. Some people did. These are really hot examples. Follow that method. They look really good. Make it look nice. Other questions? Yes.
So I chose a domestic species. How do I meet the distribution and conservation status?
What did you choose?
A domestic species?
I see. Well, I think you just have to drill into that, right? It doesn't really have a conserved status since it's been domesticated. And so you just kind of expand the human needs for the species, right? And the spatial distribution, geographic distribution might be global if they're, truly just domesticated. What's the species?
Goldfish.
Oh, yeah, goldfish. I had a feeling, yeah. Yeah. They're pretty ubiquitous, but you know what? They're invasive, right? So, people dump them in the Arboretum and other places. And so you might discuss, how goldfish are invasive and if that creates problems where they get introduced into wild areas, if they compete or they create, goldfish and carp can be ecosystem engineers sometimes, so that's an avenue you can explore.
Probably would have a distribution map, though, right?
No, you could, it's global. It's not, they don't find them in the Arctic, you don't find them in Alaska probably, but you could talk about, like, where they're invasive, where they're native to, and where they're invasive. Something like that, be creative. Okay. Extra points for creative thought, extra points for thinking outside the box. Okay, let's move on. So we were talking about gills and gill structures, how they work, and I wanted to just think a little bit about oxygen solubility. Obviously, the task for fish is to pull oxygen out of the water under difficult circumstances. The solubility of oxygen in water decreases with water temperature and with salinity. So as water gets hot, it loses oxygen. You know this from boiling water, right? In salt water, they're super challenged because there's even lower levels. So hot and saline waters have lower oxygen, and this can lead, especially more recently, to fish kills. We have fish kills in the Delta periodically. This paper was done by Andrew Ripple from here at UC Davis about the increase in fish kills recently in Wisconsin. And he was looking mostly at sunfishes, which populate these lakes in Wisconsin. And he and others calculated the historical incidence, which you can see in little red dots, and then predicted by the mid-21st century and then the late 21st century, based upon the IUCN predictions for climate change trends over the next 100 years. You can see the incidence of these sorts of kills happening. And it's a function of temperature, right? With climate change, the key thing in certain areas is just simple raising of temperature. And so in the summertime, those high temperatures prevent species from being able to get enough oxygen, and they die in massive amounts. So a note on conservation linked to physiology there. The lamellae are the little feathery structures inside the gills, and they are very thin and very, very vascularized. So they're the front of that water-blood interface, or oxygen-blood interface in the water. And the number and thickness of them varies. So in fishes that have very low metabolic demands or live in very cold oxygenated water, like ice fish here, the thickness of the lamellae tend to be quite large, and the number of them are much fewer. Whereas high energy fishes, or fishes that live in low, poorly oxygenated waters, tend to have very, very thin lamellae, because again, the more you have, and lots of them, because the more you have and the thinner they are, the more opportunities for blood to come in contact with the water. And so you can tell a lot about what kind of habitat the fish lives in just by looking at the lamellae and the gills. So these gill arches are not just for breathing. The mouth in fishes, this we'll talk about, the head structure in fishes does everything. So they also have to do their feeding structures. So the gill rakers are these structures that exist on the anterior side. So the gills are on the posterior side, like right here. These are, whoops, jump ahead. These are the gills back here on the posterior side of the gill. And these are the gill rakers facing the mouth on the anterior side. And just to go back a sec, oops, go back the other way. These feeding structures are called gill rakers, and they're used for suspension feeders or filter feeders. They often have little tiny hairs or cilia associated with them. And the thinner the gill rakers, the smaller the prey. So for a fish like an American shad, which you see down here, shad have very fine gills, arches, series of gill arches with these gill rakers in between them. They essentially, as they open their mouth, they're ram feeders, they swim through the water, they open their mouth, the zooplankton swim in, and they get trapped in the gill rakers, and then the water flows back over the gills and they absorb oxygen, all with the same structure. And I showed you this. Other fishes have really modified gill arches called pharyngeal jaws. So these are not closely spaced together like the gill rakers on a shad. This is an amberjack, which is a piscivorous fish. It's a fish predator. So they're designed to grab on. So as the fish opens its mouth, the gill rakers move in like teeth to grab the prey and move it down towards the gullet. And some species have highly developed structures called pharyngeal jaws. So you can see it. This is a moray eel. These pharyngeal jaws are attached to the skull structure and sit back behind the mouth. And they move forward when the jaw opens up. The pharyngeal jaws are attached to the bone such that they move forward, and these bony structures clamp down on the prey. Kind of like Alien, like if you saw the old movies Alien. Yeah, well, that's what they were thinking of right here. They were thinking of fish.
So almost like a second set of jaws?
Yes, well, it's, they have this. So they have the mandible and the dentary up here on the front jaws. And this is an internal, second set of jaws. Fish have really weird, highly evolved mouths. Ours are very simple in comparison. So this is one of the structures they use to help them manipulate food. And I'll get to another structure in a little bit. Yeah, question?
Maybe you just answered it. I was gonna ask like what the advantage of that is. Why wouldn't you just grab the prey with the teeth?
Well, they're in this viscous medium, right? And so the problem is when you open your mouth and then close it, that viscous medium can push the prey away. Or if you have a set of structures, you can have the water move back out through the gills and you can create a suction. So there's suction feeders, and I'll allude to this a little bit when I talk about the skull. And suction feeders have a way of pulling in the prey by opening up their mouth, and they use those pharyngeal jaws to clasp it down on it, because two jaws are better than one when you don't have hands, right? No hands, no legs, the head does it all. So skeletal structure, and I want to take a break here and talk a little bit about the skeletal structure in art. There's this guy, Adam Summers, at the University of Washington. I guess he's a prof there. And he has this technique where he basically injects a couple of dyes, Alcyon blue to stain cartilage, and alizarin red to stain the soft tissues, and then he bleaches the body of the fish so that the dyed elements jump out, and so he gets these really cool images of fish. And you can see the skeletal structure, but they're also kind of arty as well. This is our art for today. And these are just a few examples. This is a shark. He calls it shark. He calls this one a lamp sucker. It's actually a lump sucker, but he calls it a lamp sucker to be arty. And you can see like certain elements have picked up the dye, and it gives a real sense of the interior skeletal structure, including the weird jaws here. This is the palatine. This is the upper jaw. This is the mandible. They're all like, this is acanthopterygian fish, and so they all move in weird ways. But anyway, just to groove on the art, this is a really beautiful one. You can see that the ray structure of bat rays and other rays in general is really complicated, and it allows various kinds of movement in like what's often a really rigid appendage in the sharks. Electric ray, skate, bonnet head. Anyway, cool stuff. Let's talk a little bit about skull structure then, since I alluded to that earlier. So most of the complex skeletal structure of a fish is packed into that skull, and it has an unbelievable quantity, dozens and dozens of bones, are packed into, like for us, what's a really simple structure. We've got a few ear stones. We have a jaw, we have the skull itself. Fish got everything packed into the skull structure. And as I said before, it's got to be capable of handling prey capture, respiration, in some cases, breeding activities, nest making. And so all the plates in that skull tend to be flexible along really weird hinges and pulleys, essentially, that allow them to do all these things. And it's kind of like, you know, a fish skull is kind of like having like your arms and legs packed into your face. And so the first thing I want to talk about is what I mentioned to you, is this idea of a protrusible mouth. And this is another kind of riff on the whole alien theme. So here we have the same fish in the process of opening its jaw from A to B to C to D here. And what goes on? So when the mouth is closed, you can recognize the mandible here. This is kind of a superior facing mouth, right? So it's somewhat upward facing. This is the mandible, Lemmium. Change my instrument here. This is the mandible right here when it's shut. And above that are two structures. There's the maxilla, which kind of forms the upper jaw. And then there's the premaxilla, which is tucked in between, which is like the lip. It's like a fish lip. And when the fish opens its jaw, the mandible extends downward, like this one is here. And the maxilla, which is what I call the upper jaw, the maxilla has a hinge right up here at the top of the rostrum. And instead of being hinged, it also has a hinge that connects to the mandible. So when that mouth moves open, that maxilla swings forward. Here you can see it swinging forward a little bit more here. And then the premaxilla actually is shaped, has kind of upside down L shape. It's lodged. The premaxilla has a little like groove that it sits in on the top of the head. It can slide forward, and then it has a hinge that articulates with the maxilla where it swings forward. So in short, on the upper jaw, it's like an accordion. You've got two bones, and this is just the upper jaw, and they swing forward like this. And what that does is it suddenly creates a lot of negative accommodation space. And so it pulls water into the mouth structure. And at the same time, there's a series of bones called the hyomandibular and other bones that are called the suspensorium. You don't have to worry about that. Those bones are designed to go out. So they pop up off the sides of the face. The jaw goes down, the mouth goes forward. The branchiosteal rays accommodate the operculum as it flares out, and the gill arches kind of move in to grab like in towards the prey that are coming in. And so it's a very complex series of motions that are all associated with what we call suction feeding. And goldfish, sit around and stare at your goldfish doing this stuff. It's really wild once you can look at the parts. It's not just like they're sticking out their lips. Fish don't have lips. Well, not these kinds. Once you see the structures, it's really interesting. And you can probably go to YouTube as well, but go to the pet store, go to an aquarium. The other kind of feeding is called ram feeding and filter feeders. And I don't know what I had in mind there, but mostly filter feeders. I talked a little bit about this. It's just a reminder. I already talked about it. Filter feeders don't have this style of feeding. They just open their mouths, they swim forward. And primitive fish just clamp down in a very simple way. Like, and even sharks have suction feeding, but it's not as complicated as this. But ram feeders are basically their strategy, just to open up their mouth and they filter feed. The other structure in the head are otoliths. And these are worth noting because otoliths are the inner ear bones, and there's 3 pairs of them, and they're used for orienting themselves in a 3-dimensional environment. Now you and your inner ear, you have a cochlea. You also have some bones that are used for hearing, which are related to these indirectly from an evolutionary perspective. You have a cochlea that's a circular organ with lots of hairs in it, and that doesn't help you very much in a liquid medium. And so these ear stones are aligned to, they're aligned like this, and like this. So they're in 3 different dimensions. So if the fish slides this way, like when you're in like swimming in the ocean, you're underwater and you're snorkeling or something like that, and a current takes you, you don't know it until you look up and you realize the beach is where your clothes are on the beach way up the shore, because you can't detect that kind of lateral motion. Fishes can't. Between the lateral line and the otoliths, they can determine their movement or their location and their movement in the water column, which is another crazy like 7th sense that fishes have that you don't. And there's 3 different pairs. You don't need to know the names of these pairs. I don't think it's particularly useful for you, but just know that they're there. They float in a fluid and they can determine movements and their sense of equilibrium. And the cool thing about them from a scientific perspective is that they lay down rings like tree rings. So back here, this is when this fish was a baby fish and born. And if we go through, we can try and count how many years it is. This one, I'm going to guess, sometimes they also have like seasonal rings. So it takes an experienced eye, but I would call this 1, 2, 3, 4, 5, 6, 7, 8, 9. I'd say it's a 10-year-old fish. I don't know what that fish is, but I would say it's about a 10-year-old fish. And so you can determine the age of fishes using these rings. You have, unfortunately, you have to kill them, but it's really useful in stock assessment. And there's a bunch of scientists here. Yes. Yeah, that's right. There's a bunch of scientists here at UC Davis who are using these, who are taking otoliths to like a new level. Rachel Johnson, who works for National Marine Fisheries Service and has a seat at the Center for Watershed Sciences. Carson Jeffries, also Watershed Sciences, and Levi Lewis. All these people love to take student assistants, by the way. They have developed a technique where they essentially use staple isotope signatures at different points along the otolith. So going back, whoops, wrong back. So what they do is they use a laser to take a sample from different spots in a line towards the center. So they have a record of the change in stable isotope composition. And from that record, they compare it to the composition of stable isotopes in the water column from different regions. And so for like a salmon in the center, they're going to get a stable isotope reading that shows the freshwater region that this fish was born in. And then for subsequent years, it'll show a marine signature. And like, for example, one of the cool things they found is that it seems like there's a race of salmon that historically didn't go out to sea in the San Francisco, I guess the Sacramento San Joaquin River system. Most salmon go out to sea for several years and come back. Well, it turns out there was a bay run. They didn't go all the way out to the sea. And they found these in middens from Native Americans up on the Feather River. And so they determined that the signature, if the signature is the same then 100, 200 years ago, as they are now, they suggest that the bay ecosystem was so rich in resources that there was not an incentive for certain species or certain races of these fishes to go all the way out to sea. So that's just an example. They do a lot of other stuff with this. They see how much time they spend on floodplains, how much time they spend in the river while they're coming downstream. And Carson Jeffries is going to come talk to us in a few weeks about his work on floodplains. It's very interesting stuff. So that's skeletal structure in a heartbeat. I want to talk about musculature as well. Fish musculature is structurally very similar to other vertebrates. It's got 3 different kinds. There's the skeletal muscle, which is striated, voluntary muscle system. The smooth muscle, which is involuntary, that's mostly associated with the gut and also the heart. And then, oh, scratch that, sorry, mostly the gut. And then there's cardiac muscle, which is heart associated. So 3 different types of muscle, standard with vertebrates. Of note, however, that there are also 2 different types of sort of muscle fibers in the voluntary muscle system, the skeletal muscle. So red muscle is red because it contains a greater concentration of myoglobin and also hemoglobin. The myoglobin is related to hemoglobin. It stores oxygen in the muscle tissue, and it's good for swimmers, long distance swimmers, right? Or fish that have a long-term metabolic need. And white mussel, that's called slow twitch mussel. White mussel is fast twitch, tends to be the majority of locomotor muscle in fishes. And it can move quickly, but it doesn't have a lot of duration in terms of use. That muscle tires out really quickly. But it's used for short duration movements, like a striking fish is going to rely on its fast muscle. Now, certain species, because of their life history, are going to have more white muscle than they're going to have red muscle. And other species are going to have more red muscle because they're migratory species. So like, here's white mussel in a bluegill. And I'm sure if you think about it, you can think, we've talked a little bit about species that are going long distances that you could imagine are using more red muscle to maintain distance, long-term movement. And so for participation credit today, you can talk to your neighbors about this, but open up Canvas and take a few minutes and go to the participation assignment and go ahead and fill in something for this. What types of species have predominantly red muscle instead of white muscle, and why would they have it?
Yes.
Okay. Right? I still heard typing. So, speaking of muscle, I've said it's basically just like vertebrate muscle, except it isn't, right? Anyone who's cooked a fish knows that fish fillets are striated with this weird structure. And what is with that? Why is that? And so it's worth exploring for a few minutes why the skeletal structure of fishes is so unique relative to other vertebrates. And it's because they have, instead of their musculature being extended over a unique joint. So say this is like a joint. We'll just call it the leg bone, the tibia. And here's the femur. And so we have a series of muscles that extend across those. We've got adductors and flexors. And so we can extend or flex our muscle accordingly. Well, fishes don't have joints like that. They've got, most of their power, most of their musculature is associated with their vertebral column. And so rather than have those sorts of long muscles extending over a series of vertebrae, they've evolved a different structure. Let me show you that. They've got these myomeres or myotomes, as they're somewhat called. And essentially, this is the anterior end. This is the anterior end. This is the origin up here. And then this is the insertion on the other side. And the myomeres are designed to contract towards the middle in both directions. So they contract here and here in a center line, but they overlap several vertebrae. And then they're nested inside each other. So this W shape essentially fits, another W-shaped myomere fits inside the W shape of the first myomere. And they stack up like you've seen in this picture here. And so, you know, instead of when a fish swims, instead of just going like this as it thrashes through the water, instead it gets this nice sinuous S curve, which characterizes smooth swimming and allows for minimization of those sort of turbulent forces that would slow it down. It gives them a lot of control and structure, a lot of control over their particular unique structure. And so if you're into this, go check it out. Buy yourself some salmon tonight. You can cook it up. Now, if you boil it lightly, I think it works better, but you can boil it up. In between the myomeres, there's this connective tissue. And if you boil it up, you can tease apart each one of the myomeres and you can see how they fit in together. And it's kind of cool because then you can eat it. And boiled salmon, not my favorite. I like barbecue personally, but you can barbecue it and you still get the same effect if you don't savage it too much. Anyway, something for the real fishophiles of you to do. If you don't get the idea, just go check it out because it's kind of cool. All right, let's see, additional notes on fish muscles. What do I have here? 7 principal muscles. You don't need to know that, but the point is really, they have a lot of muscles in the head for opening and closing it. And you can imagine why, because I just told you about how complicated that head structure is and the jaw structure. Fin muscles have pairs. There's series of muscles, protractors that erect the fins, retractors that depress them. This is in a yellow croaker here, and you can see they've illustrated in different colors the sets of fins, and this allows the croaker. This is a pretty advanced fish, and so it has fin movement. It can lie them down, it can flare them up, it can turn them, and these sets of muscles allow them to do that. Eye muscles, same as we have pretty much. It's an evolutionary conservative organ with a supportive structure because eyes are singular. They evolved, I think they evolved once and then they radiated, but it's not like eyesight was re-evolved several times in our lineage. And then the coolest thing with musculature are the electric organs. So fish can use their muscles to contract, to create an electric charge. Not all of them, but some of them can. And essentially they've got these certain types of muscle cells that are stacked up on top of each other, and they're called electrocytes. And so this is a stingray. Excuse me. This is an electric ray. And so these muscles stack up, and when the muscles contract, it opens up the sodium channel pores, and sodium rushes in and it changes. It basically creates a highly polarized system with the polarity all in the same direction, and that can create a really strong electric field. And it hurts, like it's real, like so. It's said to be like an electric fence. Has anyone ever touched an electric fence? Yeah. A lot of you have. I thought it would be like only like the dudes who like grew up like Aggies out on the farm. You know, like I never touched one, but I peed on one once because that's what farm boys do. I'm not saying I did that. I grew up out in the country, but I mean, I know people who did. I touched it. Okay, can we just move on? It hurts. Electric fences hurt, and electrified fish, and we have a number of them. We have electric rays. I've caught them off the coast of Monterey. There are other fishes that don't have such strong electric fields as to like really injure their prey, but things like the elephant fish. This is an Amazonian fish. There's a slide of it I showed a few days ago. It has this long proboscis and it sets up an electric field around it, really to detect structure. Essentially, it's like a form of radar, only it uses electricity to detect the structure of stuff in the water column around it. Anyway, they can use it both as a sensory mechanism, a defense mechanism, and a predation mechanism. And if you got the time, I'm not going to play it, but if you got the time, you can click on this video and it'll tell you more in an amusing way with a cartoon And check it out. Oh, it's gonna play. Don't do that. Okay, we don't have time because we're gonna finish up physiology in just 2 days and move on. Kind of incredible. The notable thing about fish digestive tracts, it's not that notable, I guess, when you think about it, but fish don't really have teeth, right? So they have these pharyngeal jaws, but none of it is used in processing food. So when they, carnivorous fishes, fleshy items are easily digested. Herbivorous items are not. It takes a lot to digest. And so those fishes tend to have very, very long guts, like you see up here in the upper pages, and sometimes in the upper figure. This is herbivorous fish, and this is carnivorous fish. Sometimes carnivorous fishes or omnivorous fishes, they really don't even have a stomach. They've just got like a sac that goes straight through, like some of the minnows, because they're feeding on stuff that's either like detrital, it's basically broken down, they're just shoving it through. And sometimes, like fish that have really herbivorous lifestyles, they have these coiled intestines that you find in here. It's kind of rare though. And then some fishes have gizzards, actually. Gizzards are small organs that hold like some kind of hard objects like rocks, stones, and they use it to grind down the food before processing it. So that's all I want you to know on digestive tracts in my last, 5 minutes here. This is what kept me up last night. I was thinking about swim bladders. Every time I wake up, I'd be like, Physoclistus, swim bladders. Swim bladders use counter current exchange. There's two different types. There's the physostomatic, which they gulp water, and there's the physoclistic, where they use a counter current exchange to pump up a swim bladder. As blood flows towards the bladder, it approaches a partial pressure of the air inside the bladder, and then as it flows back out, it essentially, you know what, I can't explain it. I'm not even gonna try it. I got a few minutes. It kept me up last night every time I would wake up. So I'll let it keep you up tonight. It's a really cool thing, counter current exchange, actually producing a higher partial pressure inside the swim bladder than in the bloodstream itself. And it seemed, it's consistent with physics, but I can't explain it in 2 minutes. So a basic problem for fishes in our last 2 minutes here is that fishes are constantly wrestling with ion balance. In a marine environment, which is analogous to being a terrestrial environment, they tend to get dehydrated because the marine environment, water is going to move towards equilibrium. They're going to lose water and gain ions. Opposite problem in freshwater. They tend to fill up with fresh water. The solution for sharks is to be osmoconforming. So sharks use their body wastes, like urea, to essentially create an isotonic environment inside their body. And they don't have highly developed gills. More derived fishes, like the marine teleos, they operate hypoosmotically. They're constantly losing water. They drink seawater, and they have special chloride cells to remove from their body. Freshwater teleos have the opposite problems. They're operating hyperosmotically, and so they have super well-developed kidneys to try to excrete the water. Final points. I just talked about these things. I'll let you review them. Internal anatomy. Here's what I need you to know. Fish muscles, like that of other vertebrates, there's 3 different types. There's white muscle, there's red muscle. The heart system I didn't talk about, so I guess you don't need to know much about it. The digestive tract differs based upon what they eat. Kidneys, osmoregulation, please go back and figure that out. If you have questions, shoot them to me. I can address it in the next lecture. Lateral lines, we talked about lateral lines last time, and swim bladder, physoclistic swim bladder. Let it torture you like it tortured me. Thank you.